Okay, welcome everybody. Today we're going to discuss the states of matter, and by the end of this lesson, you should be able to tell how the states of matter are similar and how they're different. So we're going to discuss three states of matter: solid, liquid, and gas. There is a fourth state of matter known as plasma, but since we're not going to observe that, we're going to concern ourselves with solids, liquids, and gases. Now, all three of the states of matter are made up of particles that have mass and take up space. The measurement of the space something takes up is volume. So we could say that all of the states of matter, all matter, has mass and volume, okay? Now, there are some ways in which the states of matter are similar, but there are lots of ways in which the states of matter are different. So they can differ in terms of their structure, whether or not their particles are put in a certain order, or if they're just kind of moving around, compressibility, whether or not the particles can be moved closer to each other, basically how much it can be squeezed. Volume, whether they have a certain volume or if their volume can change. Their shape, whether they have their own shape or if they take the shape of their container. They have varying amounts of kinetic energy, which, if you'll remember back in middle school, is the energy of movement. And they're also different in terms of intermolecular forces. And I know that's kind of an intimidating word, but intermolecular forces is just the attraction between particles. So how much are those particles attracted to each other? I'll tell you now that that depends a lot on how close they are to each other. When they're closer to each other, they exert more of a force of attraction to the particles around them, okay? So first up, we're going to talk about solids, okay? So solids have an ordered structure. So if you look at this picture here, each of those particles, and I'm guessing this would be an element because it looks like single atoms and all the particles are identical, they are in a specific order. It looks like they're all lined up like little soldiers. In this picture right here, it looks like they kind of alternate a little bit, but still there's an order. There's a pattern to the way that these atoms or molecules are arranged, okay? So we say that their structure is ordered. They are not compressible because the particles are already very, very close to each other. So we're not going to be able to squeeze them closer. They have what we call a definite volume. They are not going to change their volume. They're not going to swell to fill their container. Whatever their volume is, it's going to stay the same unless we perform some sort of physical change like cutting it, okay? Solids have the least kinetic energy in their particles. That's because they're stuck pretty much in the same spot. The particles are so close to each other that they're not moving much. So since they're not moving, they don't have a lot of kinetic energy. Solids have a definite shape. They come in a certain shape, and whether I take it and put it in a different container, that shape is not going to change. So if I, for example, my Post-it notes here, they're a solid. If I take my Post-it notes and move them from one drawer to a different drawer, they're still going to be the same shape, okay? And because solid particles are so close to each other, they do have quite a bit of intermolecular force between particles. Again, the closer these particles are to each other, the more attracted they are to each other. So solids have the greatest amount of intermolecular forces because their particles are the closest. Okay, so the next state of matter is liquids, okay? If you see, the picture's a little bit different here. So for liquids, we say that their structure is fluid. We say that it's fluid because they're not in any certain order. Those particles are kind of moving around, okay? And because those particles are moving around, definitely more so than in a solid, we say that their kinetic energy is greater than solids, but it's going to end up being less than gases. Okay, so the particles are moving, but not as much as gases. We'll talk about that. Still, the particles are pretty close to each other. So in terms of compressibility, we're going to say no. Liquids are not compressible. Okay. Their volume is definite. So if you think about it for a second, if I have 100 milliliters of water in a graduated cylinder and I pour that into a beaker, it's still going to measure 100 milliliters of water. The volume is not going to change even though I've moved it to a different container. However, the shape will. If I take a liquid and move it from one container to another, it takes the shape of the container. And you can see in this picture that the liquid particles are spread out along the bottom. Whatever the shape of the container is, the liquid is going to take that shape. So we call the shape indefinite. And liquid particles, because they are pretty close together, do have some intermolecular forces. Now if we talk about gases, the last state of matter, you can see in the picture that they're very different. And we can see right away that the particles have little arrows where they're moving. So one of the things about gases that's very important is that they have the most kinetic energy of any of the states of matter. We call the structure fluid because those particles are moving and not in any certain order. Because the particles are pretty far apart from each other, gases are compressible. And you'll find compressed gases in a lot of places, like propane. If you go to the store and you get a propane tank, it sounds like a liquid in there, but really propane is a gas. What happens is that gas, propane, is compressed to a point where the particles become so close to each other that it becomes a liquid inside the tank. So yes, gases can be compressed, and at some point, they'll be compressed to a liquid. The volume is indefinite. Gases will swell up to fill any container. If you blow up a balloon, the carbon dioxide in the balloon isn't going to stay on one side of the balloon. It's going to spread out throughout the balloon, and those particles are going to bounce around in there. And because those particles are constantly moving, they have an indefinite shape. They will take the shape of whatever container they're put in, okay? Or think about a balloon that can be bent into different shapes, right? It's full of gas, and it can be shaped any which way you want, okay? Because the particles are so far apart from each other, we say that gases do not experience intermolecular forces. These particles are just too far apart to exert any force of attraction between them, okay? Now, another thing about the states of matter that's very important is that they can be changed, okay? And first off, all phase changes, all changes to the state of matter. If I go from gas to solid, or solid to liquid, or liquid to gas, or any combination, all phase changes are physical changes. These molecules themselves remain unchanged. What is changing is the amount of space between them, the amount of kinetic energy they have, etc. Okay? So we'll start with some that are very familiar to us. If a sample of matter is a gas and we compress it to a liquid, when it goes through that change, that is known as condensation. And a lot of times you'll observe that phase change in the morning. You'll see the dew on the grass or the liquid on your windshield on your car. That is the water vapor from the air condensing on those materials. Okay, it's going from a gas to a liquid. Now if we go the other way around, so in the afternoon when it heats up, vaporization occurs. Can also be called evaporation. It's the same thing. We're going from a liquid to a gas. Now, when something goes from a gas to a liquid, we are moving those particles closer together. And since the particles are becoming closer together, they're going to exert more force on each other. So we're actually going to increase the intermolecular forces between those particles. So condensation will form intermolecular forces between those particles. However, if we go from liquid to gas, all of a sudden the particles are further apart from each other and there are fewer intermolecular forces there. So that's vaporization. It takes energy to break those intermolecular forces. In order to move those particles away from each other, because there's a force of attraction there, you need a force to do that. So that's why usually it takes energy, right? It takes heat energy to evaporate something. Meanwhile, if you lose heat energy, then condensation occurs. So you allow those particles to exert that force of attraction on each other. So that does not require energy. In fact, you have to take energy away from the surroundings in order to get that to happen. So condensation allows those intermolecular forces to develop, okay? Similarly, if a liquid goes to a solid, that's known as freezing. And again, we're moving the particles closer to each other, and when those particles are closer to each other, more intermolecular forces develop, okay? And since intermolecular forces develop naturally, then the material is losing heat energy at that point. Now, if we take a solid sample and we add heat energy to it, that will break those molecules away from each other, break those intermolecular forces. And we call that melting, okay? So melting moves the particles away from each other, and freezing moves them closer. So in melting, we're breaking intermolecular forces, and in freezing, they're forming. And then lesser known changes of state are from solid to liquid, or I'm sorry, solid to gas, and vice versa. So when a gas becomes a solid, this is known as deposition. Okay, that material is being deposited as a solid onto something, okay? Sometimes that'll happen whenever you have something really cold, and I'm thinking about a very cold pipe or piece of metal. Sometimes the water vapor will skip the liquid phase and will just freeze to that super cool piece of metal, and you'll notice like frost on it, okay? If the opposite happens, if a solid goes straight to the gas phase, that's known as sublimation. And we discussed that earlier in the week when we talked about dry ice. Dry ice goes from the solid phase straight to gaseous carbon dioxide. And again, when we're breaking intermolecular forces, we're moving those particles further from each other. So when we do that going from solid to gas, there's going to be a lot of intermolecular force broken. Okay, so a lot of energy is being gained as something goes straight from solid to gas. So sublimation will require energy, a lot of it, in order to break the intermolecular forces of the solid and go straight to gas. Meanwhile, the attraction between particles is going to increase greatly when we go from solid to gas. This should complete your notes, and what you guys need to do for full credit is make sure that you write a complete summary that answers this essential question here. So you guys need to give me 1 or 2 sentences that describes how the states of matter are similar and how they're different. So this is going to be part of what I check tomorrow.